All right, here goes. So we've got this variable y equals ln sec squared x plus cosec squared x between an interval. Students asked to get this as the derivative, and then they attempt this proof to get the correct answer, but we have to identify the error in the proof. And the error is here to here. So identify the student has used ln a plus b equals ln a plus ln b. This is not generally true. Now this is an interesting question because actually for this particular function, it turns out that it is true. You can separate it, but it's only because of certain properties that it has, and that's kind of something that this question then goes into. So that's the answer to part A. We're asked in part B to give a correct version of the proof. So we're starting with this, and we're trying to get to minus 4 cot 2x. So this is part B. Okay, now you've got to be a little bit careful here because I've got to be honest, when I did this, I did get an answer, but I couldn't simplify it to minus 4 cot 2x. The way I did it was actually to use the chain rule on this directly. You have to differentiate sec squared and cosec squared, but you just get lots of trig functions basically. It must cancel down, but it's very hard to see how. So actually, the little trick to this that is going to speed things up. I mean, if you want to try and do it that way and you get there, fair play. But there's a little easier route that you can do. And it is actually to write it in terms of sort of more normal, more typical trig functions. So 1 over cos squared x plus 1 over sine squared x. And then add these together. So we're going to cross multiply. We're going to get sine squared x plus cos squared x all over sine squared x times cos squared x. So basically I've got a common denominator sine squared, cos squared. I've just had to times appropriately this one by sine squared top and bottom, this one by cos squared top and bottom. This is brilliant because the top is identical to 1. We can use that identity. So it's going to be ln 1 over, actually I won't rush it, 1 over sine squared x cos squared x. We can actually write this as ln 1 over sine x cos x all squared. Why would you want to do that? Because now you can write it as ln sine x cos x. Actually, I don't think I need this bracket here at all to the minus 2 because we got the reciprocal and we got the 2, so it's minus 2. So then we can bring the minus 2 out using the third rule of logs and write it as minus 2 ln. We haven't even started differentiating yet, but you can kind of see it's getting a little bit simpler. And now actually, if you can recognize that this is use double angle formulae, this is actually a half. So sine 2x is 2 sine x cos x. So this is going to be a half sine 2x. This is fantastic. It's such a simpler function than, well, seemingly than what we had at the start. I mean, they're identical, but that is going to be much tougher to deal with. Okay, this is brilliant. So now we can do dy by dx. Actually, there's one other thing I'm going to do. Sorry, I'm gonna get rid of that. So I'm going to use the first rule of logs when you're timesing them inside the log, so you can add them. So it's going to be minus 2 ln a half minus 2 ln sine 2x. So now dy by dx, the reason I've done this is that when I differentiate this, it just disappears. Actually, it's just to remind you really that if you differentiate ln kx, then you still get 1 over x, because you can either separate it as ln k plus ln x, or you can use a chain rule, and then you get you differentiate this and you get k, and you get k over kx, which simplifies to 1 over x. So we can just ignore this when we differentiate, and I'm going to get minus 2, and then when I differentiate, I've got ln sine 2x, so I differentiate the sine 2x to give me cos 2x, and it's going to be all over sine 2x. So I've used a chain rule there. I'm not going to go into any more detail for that. So that gives me minus 4 cos 2x over sine 2x, and this is precisely minus 4 cot 2x, which is what we wanted to get at, from the start. Okay, looking at part C now, find and simplify a general relationship between P and Q, where P and Q are essentially functions of x, such that the student would obtain the correct result when differentiating ln P plus Q with respect to x by using the incorrect method. So i.e. using the fact that ln P plus Q equals ln P plus ln Q. And that is what they've assumed. And so for it to work, we need that d by dx of the left-hand side is equal to d by dx of the right-hand side. So we require d by dx. Remember, P and Q are functions of x. Technically, I could put this, I could write ln P. I could separate it to differentiate them separately. Sorry, I'm going to put it on a different line actually. Okay, there's two ways to do this. There's the quick way, which actually I missed when I did it, and there's a longer way. It's more complicated, but still gets you there. Okay, quick way is so this is what we require, and we have a differential, differentiating going on both sides. Now, the long way is to actually differentiate to start with. The quick way is to realize that, you know what, we've got two derivatives, so we can integrate both sides with respect to x. And we are differentiating and then integrating, so we get back to the original functions, except we also get a constant. Now, so I'm just going to emphasize that. We can let C equal ln of some other constant. There's nothing stopping us doing that, because then we can start bringing it all together. And that will in fact equal ln APQ, which means we can undo the logs and actually that would be a possible answer. We've got a relationship between P and Q, and I should probably, did I say that A was a constant? A equals arbitrary constant. Now I think we can neaten this slightly because we can divide through. So A is going to be P plus Q over PQ, which actually, if you simplify it, becomes 1 over Q plus 1 over P. And in our words, the reciprocals, the functions, add or sum to give a constant. Which is indeed the case for the student's function. Because if you take the reciprocal of sec squared, you get cos squared. Take the reciprocal of cosec squared, you get sine squared. If you add them, then you get 1. So that's why it works for those two functions. And it will work for other functions as well, potentially. Just going to talk you through the longer route. I'm not saying you should do it this way, but if you didn't spot to integrate straight away, okay, then we're back to here. We actually have to differentiate. It's not a good method actually in hindsight, but hey. So if we differentiate the left-hand side, well, we differentiate what's inside the bracket, we're going to get P dash plus Q dash all over P plus Q. And that's then going to equal P dash over P. We differentiate ln P plus Q dash over Q. I can now multiply through by each of these three terms. So I'm going to get P, Q, P dash plus Q dash. I've times through by P, Q times P plus Q. So that's cancelled and I'm just left with P, Q times the numerator. And then over here, I'm going to have P plus Q. When I times this by what I just said, the denominators, I'm going to get P dash Q. And over here, I'm going to get Q dash P. I hope that makes sense. Right, need to multiply this out. Now I'm dealing with the Q. Okay, we've got P, Q, P dash. That's actually on both sides. P, Q, Q dash is here. Okay, and I could minus this from both sides. And then I could write it in as dq by dx. And dp by dx. Not saying you want to do this way, I've already said that, but it will work out. Okay, now we've got derivatives on both sides and p's and q's. Well, I can't do it. I can't really do anything with that yet. I can't integrate both sides. But what we can do is essentially the same as separation of variables. I can get the p's all on the right hand side and the q's all on the left hand side. And now we can integrate. With respect to x. So using the chain rule, this is actually just dp, and this is dq. Okay, increase power by 1, divide by the new power. Do the same here. Going to get a double negative. And then I've got a plus a as well. I can then write that 1 over p plus 1 over q is equal to minus a, or just some other constant k, and we do have the same answer. So a lot more work, but we got there that way as well. On to the final part of this question, which is no less awkward, if I'm being honest. So it's quite interesting now, because now we're given a different set of functions p and q. We've got cosec squared, but now it's k sec rx. And we're interested in finding the values of k and r such that it will satisfy the relationship from part C. The good news is we have this relationship from part C, the fact that when you add the reciprocals you just get a constant. So let's substitute in. So set 1 over k sec rx plus 1 over cosec squared x equal to a constant. Now I'm definitely not going to call it k because I've got a k here now, so let's stick with capital A. That means I want to get rid of these secs and cosecs because I've got reciprocals of reciprocal trig functions, so I can write 1 over k, and then sec rx, 1 over sec rx is simply cos rx, and then this one's going to be sine squared x. Remember, I'm trying to get a relationship, I'm trying to work out the values of k and r for this to work. So I don't really want a sine squared there. So my first thought when I was doing this question actually was to try and change this to 1 minus cos squared x. I'm going to write down what that gives. Because now, remember, a is just a constant. So if we minus 1 from both sides, it's just going to be a different constant. B is equal to a minus 1. How does that help us get r and get k? Well, the thing you've got to realize now is your double angle formula, because we've got cos rx. Remember, there's a double angle formula, cos 2x, and there's 3 different ways you can write it. Standard result is here. But if you substitute in for sine squared, 1 minus cos squared, we get 2 cos squared x minus 1. And that means that cos squared x is actually identical to, I can divide through by 2 and then add the half. It's a half plus a half cos 2x. So this means 1 over k cos rx minus half cos 2x. This will equal like a new constant. Sorry, I'm introducing another one. I'll call it capital D, because what have I done? I have replaced this by this. So I'm minusing the half cos 2x. I'm actually minusing the half, so I just added the half to both sides. D is then b plus a half. This is true for all x, remember that. So we can actually take this function and differentiate it, because I don't really want, like, I can't do anything quite at the moment. So when I differentiate, I'm going to get minus r over k sine rx plus sine 2x. That is going to equal 0. This tells me that r must equal 2 for this to happen. Yeah, technically this is an identity. R is equal to 2. And k must also equal 2 to make this minus 1, which then cancels with it. That's how I did that question. The mark scheme does it very slightly differently. Just going to bring it up, in fact. So they write down this result from C, manipulate it, seem to avoid having to differentiate, but they do get the same answer. Well done if you got that. I thought that was awkward. Okay, well done.